Hey everybody, this is John Buck. Welcome back to another array signal processing video. And in today's video, I'm going to talk about a technique for making adaptive beamformers more robust that is known as covariance matrix tapers. And the idea behind this is that by adding a simple small step of processing to our estimated spatial covariance matrix, we can create beam patterns for our adaptive beamformers where the beam patterns have notches that are a little bit wider. In fact, we can control how much wider we want to make them. And in doing that, make our beamformer more robust to any imperfections. Right? We've seen that adaptive beamformers make beautiful deep nulls in the location of interferers when they get them right, but those nulls are also very sharp, which means if you're off by a little bit due to some measurement error or some inconsistency or imperfection in your measured data between where you're estimating the interferer is and where it really is, you may lose a lot of effectiveness because those nulls are so sharp. So there are times where it would be helpful to have the null be a little wider. And covariance matrix tapers is a very good way to do that without paying a huge cost in computation or performance. So let me switch over to the whiteboard and I will give you a quick overview of how covariance matrix tapers work. In the overview I'm going to give you today is sort of drawing on three previous publications from the mid to late 90s. Mailloux and Zatman published papers about 6 months apart in electronic letters that were sort of just 1 to 2 page short letters. And then Guerci published a paper about 4 years later in IEEE Transactions on Signal Processing that sort of synthesized all these ideas together and also expanded them into space-time processing, which is sort of the adaptive version of the k omega processing we saw last time, when we allow things to be adaptive both in spatial dimensions and in time dimensions. But what I'm going to tell you today is give you a brief overview of how to apply covariance matrix tapers, and then in class we'll talk some more about deeper insights conceptually of how they work or why they work. Okay, so let's move on to the next page. Moving into the details. I need to scroll that down a little bit. Covariance matrix tapers start from the idea, coming back to fundamentals of the array manifold vector, right? The idea that for a plane wave coming from direction k sub z, the nth element of the manifold vector will look like this. And this is sort of implicitly for a uniform line array, right? The fact that the sensor location is d times n, and we're going to assume today that n is this center symmetric version, right, where nc is the total number of elements in the array minus 1 over 2. Right, so that we're counting through that, assuming an odd number of elements in the array. And we can take this a step further and say, well, all of what's going on up here, what really affects the narrowband beamformer comes down to a phase term. So we could write this, let me make it a little clear that n is a multiply, not a subscript. We could write this as some phase term phi, right, e to the minus j times phi of n, where phi is equal to the phase here. I do want to put that over on the right. Just a second. Okay, so that phi term is kz times d, and if I can expand kz out in terms of more direct things like frequency, we can say, well, kz is the lead k0, which is 2 pi over lambda, which is also 2 pi frequency over the speed of propagation, times d, and times the cosine of the bearing for the plane wave, right? Cosine of theta. So in real life, we have to recognize that our data may be noisy, and that as we collect a bunch of snapshots to make the sample covariance matrix to use in our SMI or diagonally loaded versions, that things like theta may be jittering over time. It may not be, the interferer may not be perfectly still. Often things moving in the atmosphere or the water, even if they're not moving that much, are sort of vibrating, or maybe jittering as they're fighting a current or the wind or something like that. And these other factors could be time varying or slightly off from our assumptions too, which means we end up saying it. We could model that as saying, instead of the true phase, why don't we say maybe there's a phase error or phase jitter. So that's this term here. So we replace what we assume was the true phase, because this is what adaptive beamformer is going to use to locate the null, right? This phase as we go from sensor to sensor, effectively, or this is really, I guess, Guerci calls it phi. We should have called this psi. I'm going to do that because that's more consistent with Van trees. Hang on, I'll be right back. All right, so that's a little better. I apologize for the quick change in notation, but I did want to fix that before I went any further. But so, Van Trees has already said kz times d, we define that to be psi, or I guess this should be minus psi, but the minus signs are not important for what we're doing today. So we'll live with this definition for now. But again, the main idea is that imperfections or time variations, small time variations among any of these factors could lead to small amounts of jitter as I measure snapshots. And so that psi should really be placed by some psi tilde, where again, to be clear, this tilde is just expressing the fact that it's a perturbation or an error. This is not, I was just realizing, we sometimes use the tilde earlier this semester to represent a whitened coordinate frame. And we're not whitening anything here. I'm just using that as a notation to represent a small error or a jitter for that. And so we're going to assume that that phase jitter, psi tilde, is random, that it's uniform between so we don't know exactly what it is, but we can put an upper bound on how much of it there will be. So we'll say we know the phase is going to jitter plus or minus some amount delta. And we'll also assume it's independent or uncorrelated with the real signals and the other noise, the real signals and the additive noise. So let's see how we bring that into our model, right? We say normally when we assume if I'm observing data with a bunch of signals present, a snapshot, say the nth snapshot, might be a sum of a bunch of signals, each of which has its own random amplitude and a manifold vector associated with, I'll just call it, for the dth signal, we'll just sort of use a shorthand and say this is the manifold for that one, plus some amount of noise, right? Some amount of additive noise. And so we would use these normally to get to our sample covariance matrix. So what we're going to do now is look at how we could take that tapering into account, or how we could consider that noise as a kind of random shading taper, random taper vector, random shading, right? That we could say if I have a manifold vector for the k sub z direction, the nth element of it, like we just said, was originally e to the j psi, but now I've got psi plus psi tilde of n. And using the rules of exponentials, I can take that sum in the exponent and turn it into a product of exponentials. And why this is important is this says I've now got two pieces. One is the true signal, or maybe it's the measured signal, and then this is the jitter term, which is now disconnected from anything that's part of the real thing, right? This is a random phase that's getting added in, but it doesn't depend. It'll turn out to be important that it's independent of all these terms and it's disconnected. So if I think larger, if I define a taper vector t tilde, little t tilde, to be equal to e to the minus j psi of n, which in a weird way is almost like it's like the manifold for the psi tilde direction, right? So the nth element of this vector looks like this. So I guess we should make that clear. So the nth element has this form. Then I can write, I can think of my measurement x is going to be, or maybe the modified version of the measurement is going to be an element by element product of t tilde times the actual x I measured. I'm going to take the real signal and then apply this, where the dot in the middle represents what's called a Hadamard multiply. which in MATLAB term, maybe the easiest, quickest way to say is this is like dot times in MATLAB. So it's an element by element multiplication. So we're going to take our data and basically apply these phase jitters to it. And so when we do that, we'll see, let's think about what happens to our covariance matrix. Right, we'd say it in, wrong color. Our covariance matrix is the expected value of x tilde Hermitian. And so that would be the expected value. And now I plug this in. So I've got T tilde Hadamard x times the same thing, the outer product of the same thing with itself. Right? And so if I think about this, this is complicated at first, but if I think about it term by term, let's call this what we've been calling things. This would be S of x, right? We call it S tilde. Right, so this sort of jittered version of the phase matrix, and I go look at the mnth element, I can use the properties of this to say, well, this would be T tilde m x sub m times, well, it still has the expected value out front, times the, let's see, the column is n, so I get the column out of these ones. So I have T tilde of n times x of n. And now I can regroup things within that expected value. And so I'll bring the t's together, the t tildes together, and the x's together. Right, so let me see, the mnth element looks like this. And now pause for a minute and say, well, what did I assume about the phase that creates these versus all the other random things in this signal? Pause the video for a minute, test your memory. Right, I assume they're independent. So if they're independent, if I have an expected value of a product of independent things, what can I do with that? Yes, I can write it as the product of expectations because the phase error is independent. So this is the expected value over the phase error, or the sort of random taper term. This is the phase jitter taper. So it's not, I mean, mathematically it's acting like the tapers we saw earlier, like Hamming and Hanning, but it's a very different thing because it's a random vector here. And this is the expected value over all the normal things, like the amplitudes and the noise and all that. And this, again, is hugely important that this jitter is independent of where things are actually from. And so if we look at this, we say, well, the right-hand side is the original S of x. Right? This is our spatial covariance matrix for the true signal. And then we have this term here, and we're going to call this, just to give it a name that's similar, this is capital T. So it's saying the mnth element of the tapered or jittered covariance matrix is going to be, well, the mnth element of this T times this is the mnth element of, so this is, well, S of x mn, and this is the mnth element of this new matrix T. Right, so I can write that whole thing more compactly and define this T vector as well to say that the jittered spatial covariance matrix is the covariance matrix taper. That's where the name comes from. This capital T Hadamard product with the original covariance matrix, Sx. Or these could be, you could write this as Sn if it's signal absent, I guess. Where T is defined to be the expected value of this term, which would be e to the minus j psi m, and then I forgot, these second ones are from the Hermitian, the ends, so these are all conjugates, right? Because the Hermitian is the conjugate transpose. So the second term, the conjugate flips the sign, and I get this. And so capital T is in that form. And so it's the expected value of, and these are the tildes, of psi tilde n minus m, expected value over the psi tilde. Okay, so in class we'll see how to get through this, but let me just quickly put the answer here, because I'm conscious this video is running longer than I intended. So this taper, this is the covariance matrix taper, capital T, that we multiply the Hadamard product with, is a sinc function. So it turns out an n minus m in a matrix are along the diagonal, so are along sort of super subdiagonal. So well, it'll be 1 on the main diagonal, and then you'll have sinc of delta for when n is 1 greater than 1 or minus 1. So these will be constant. This will be a Toeplitz matrix, constant along the diagonals for the covariance matrix. So it preserves that property of the true covariance matrix. It still implies the Toeplitz. The Guerci paper, which I think has the biggest, the most general overall view, also explains how you can include a term in this so that when you Hadamard product with T, you're getting diagonal loading as well. So you can get some diagonal loading to stabilize things and broaden the nulls. And we'll do this as a class problem to see how this works out, as well as build some more insight into how it works. I wanted to finish by showing you some examples. Oh, well, so let me again first tell you how the process works, how this turns into a beamformer. So in practice, you first observe the k snapshots of data. So the next step then is to average those snapshots, those k snapshots, to get an estimate of the sample covariance matrix. The next step after that is to taper the whole sample covariance matrix, so this should be S hat, with T to get S tilde. So this is and this is why this is called the covariance matrix taper. It's just an element by element matrix, multiply of every element in the matrix with this thing that is the diagonal matrix of sinc functions, right? If we wrote that out, the taper matrix would look something like this with 1s on the diagonal, sinc delta above and below it, because sinc is an even function. These are, I guess one of these is really sinc of minus delta, but because it's even, it has the same value. Sinc of 2 delta and so on, going out, each of these going straight down the diagonal. So this is our taper matrix. Then the next step is to compute our weight vector. Right, so the direction of the weights are determined by S tilde inverse V naught, and then this alpha out front is just a constant to set the gain to be 1 in the look direction of V naught. So it's V naught Hermitian, S tilde inverse V naught. And so this is the way we would do it. And in practice, as I mentioned, the Guerci paper tells you how you can choose T to both include the sinc term and also include some diagonal loading at the same time to get the good properties of that. So let me finish by showing a couple examples of how this shows up in the beam pattern from some of the papers I mentioned at the start. If we look at the Guerci paper, this is the angle. This, I guess, what would this be? This is this is like u over 2 on this axis. This is d over lambda times sine. So they've taken the pi out, and it runs from minus 1/2 to plus 1/2. This is a beamformer with a loud jammer at 60 dB INR at an angle of minus 30 degrees. So that would be here. It works out to be minus 1/4. So yeah, this is like sine over 2, I guess. And so they've already shaded with a Chebyshev polynomial to get minus 30 dB. So this is the ensemble result. If we knew the true covariance matrix, we get a nice deep jammer null here. But one of the problems that we see is that with the sample covariance matrix in B, with twice as many snapshots as sensors, is the side lobes have come up about 20 dB. This is what the poor white noise gain looks like in this domain. The jammer is still there, but we've really lost a lot of white noise gain, which is shown in the increased side lobes. By adding some diagonal loading, the side lobes come back down, things start to look better, and we still have this deep jammer null. But again, if it's not in exactly the right place, if the jammer is moving a little bit, it won't work well. So in this last one, the delta added was just 0.01, so like a 1% jitter. And this, we can see the notch is much wider here, so it's much more tolerant of any jitter or imperfections in the measurement. So that's even with just a little bit of jitter, it makes the wider jammer, and it's kept the diagonal loading part, so it keeps that down as well. This is from Zatman's paper in 1995, a similar type comparison. The dashed line is the original adaptive beamformer. This had two interferers, one about here at 0.3, the other one at 0.8. This is essentially a U-axis, though it's not showing the whole axis. He's just zooming in on the region with the interferers. And so by adding, he calls it dispersion in that original paper for this 64-element array, but has basically made delta wide enough to significantly widen the notch, much more than Guerci did. I think this was equivalent to 3 bands. The delta was equivalent to 3 bands. You can see there's a much wider notch here. So what was the original one with a little bit of diagonal loading gave us what's the conventional dashed line here. We have a very narrow notch. By adding the covariance matrix taper, Zatman was able to make a much broader notch. All right, so I'll finish here. That's an overview. We'll talk more about how and why this works and to give a better conceptual understanding in class on Monday night. So that's all for now. Have a good time, or have a good day, and I will see you next time.